It's Workbench from Workbench Quagmire. Welcome back to our free code camp Python certification in 100-ish days. It's day 83. 17 days left. I think we'll make it probably in less than 100 days because we're going to do the reviews and stuff. Excuse me. So we just have a few more theory sections to work through here, and then we'll get into some of our workshops and labs for this graph section. Understanding graphs and trees. So let's get started with how do matrices and adjacency list work. Graphs are very powerful data structures made by a set of nodes, also known as vertices, and edges that connect them. Here are the two common ways to implement graphs in your code: adjacent matrices and adjacent lists. Let's look more into these and go over their advantages and limitations. So adjacent matrices, let's start with adjacent matrices. An adjacent matrix is a two-dimensional list in which the rows and columns represent the graph's vertices. The value in the matrix represents the edges or connectors between the nodes. For example, if you have a matrix stored in a variable named matrix, the value stored at the matrix ij, or where j and I row, where I is the row and j is the column, represents the edge or connection between node I and j. The values may have different meanings depending on whether the graph is weighted or unweighted. In a graph, if the graph is unweighted, a value of 1 means there is an edge connecting these nodes, while a value of 0 means there are no edge between them. If the graph is weighted, the value would represent the weight of the edge that connects the nodes. One of the great advantages of using a adjacency matrix, that is checking if there is an edge between two nodes, takes constant time, big O of 1. This is because the program only needs to find that particular value in the 2D list. However, this efficiency in finding the edges comes with a trade-off. Adjacency matrices have a large quadratic space requirement, so v squared, where v is the number of nodes in the graph. This is inefficient for sparse graphs, which are graphs that only have a few edges. Why? Because if the graph is sparse, you have to store many zeros in the matrix to represent the lack of edges between the nodes, and these nodes and these zeros will still take space and memory. Adjacency matrices are also inefficient for finding a node's neighbors because the program has to iterate over the entire row or column to find zeros and ones that represent the edges. In the worst case, this process can take v time, or it's linear, where v is the number of nodes in the graph. Let's see an example of an adjacent matrix for this particular graph. So we have nodes A, B, C, and D. We have edges from A to C, A to B, and A to D, and from B to D. So in this adjacency matrix, each row represents a node. The first row represents node A, and the second row represents node B, and so on. Each column represents a node also. Each value in the matrix represents whether there is an edge between each pair of nodes. A value of 0 means there isn't an edge connecting the nodes, while a value of 1 means there is an edge. The values in the diagonal represent whether or not each node has a self loop, an edge that connects the node to itself, or in our example, they are all zeros because the graph doesn't have any self loops. This visual representation of the adjacency matrix to show you how this is a visual representation of adjacency matrix to show you how the rows and columns represent the corresponding nodes. For example, the first row is 0, 1, 1, 1 because node A has edges connecting it to node B, C, and D. You see there, 3 edges. And then row 2, there's only a connection to A, or an edge with A and D. and so on here, as this is the same adjacency matrix but implemented in Python code. So we have a list with a bunch of lists, or 4 lists basically, for rows and columns. Adjacency list. Another common way to represent graphs is by using adjacency lists. An adjacency list is an array or dictionary that stores all the neighbors of each node. There are 2 ways to implement adjacency lists: as an array, where each index represents a node and the list stored at the index contains its neighbors; as a dictionary, where each key represents a node and the values associated to the key contain its neighbors. Adjacency lists are more efficient than adjacency matrices in terms of space requirements. They have a 0, or a big O, of V plus E space complexity, where V is the number of vertices and E is the number of edges. It's also efficient for finding all neighbor nodes, since this operation only requires assessing the list associated to the node. However, there is a trade-off. Adjacency lists are less efficient than adjacency matrices for determining if an edge is an edge between 2 nodes. Determining if there's an edge between 2 nodes. The search process can take linear time in the worst case, since it may have to search through a very long list of neighbors if the node is connected to all the other nodes in the graph. Here is a example of an adjacency list for this graph. I keep saying graphed. The adjacency list is implemented as a dictionary. Every key in the dictionary represents a node, and the values associated to the key is a list of all the neighbors for the corresponding node. So we have a dictionary with our key A, B, C, and D, and then we have a list with the adjacent nodes. Alternatively, we can implement it in a 2D list in which the index represents a node. For example, 0 represents A, 1 represents B, and so on. And then each of those lists just has the neighbors. So neighbors for A, B, C, and D. Notice that even if this 2D list may look similar to the adjacency matrix, they are quite different. The adjacency matrix stores 0s and 1s and other values that represent the edges or weights of the edges in the graph. The adjacency list stores the actual list of all the neighbors of each node. This is a very important difference that you should be familiar with. Both adjacency matrices and adjacency lists are very important for implementing graphs. Choose between them. Depends on the graph size and how you need to use the data. Adjacency matrices are helpful for dense graphs with many edges, while adjacency lists are usually preferred for choice of real-world scenarios where sparse graphs are more common. So, our quiz: for which of the following scenarios is an adjacency matrix the more efficient choice for representing a graph? So, a social network with billions of people and very few connections per person. That's not true. A computer network with only 5 connections. That may be true. A dense graph where every node is connected to almost every other node. I think that is going to be our winner. A graph where the main operation is to find all the neighbors of a specific node. Nope. When would it be more efficient to use an adjacency list over an adjacency matrix? When the graph is dense? No. When you need to check if an edge exists between 2 nodes very quickly? I think that's true. When the graph has a high number of vertices and many connections? That's not true. When a graph is sparse with a high number of vertices and a low number of edges? I think that's probably our best choice. And which of the following operation is faster in an adjacency matrix compared to the adjacency list? Finding all the neighbors of a single node? Nope. Checking if a direct edge exists between 2 specific nodes? I think that's our choice. And iterating through all the nodes in the graph? That's not true. And adding new nodes to the graph. So I think let's see how we did. Boom. Okay. We'll do this one, and then we'll finish up tomorrow with the last theory section, probably a short video. What are the trees and tries? What are trees and tries, and how do they work? Trees are very important to the world of computer science. A tree is a specific type of graph. For a graph to be classified as a tree, it must have no loops or cycles, paths where the start and end nodes are the same, be connected. Every node can be reached from every other node. Trees are nonlinear data structures that organize nodes in a hierarchy where nodes may have children, siblings, and parents. The root node is the very top of the tree, is the only node in the tree without a parent node. This is the node where you will start traversing the entire data structure, usually with algorithms like breadth first or depth first, DFS. Here's a graphical example of a tree, A, B, A, C, C, D, C, E. Since the nodes are organized in a hierarchy, they have a relationship between them. Parent node is a node that immediately connects to the other nodes below it. In this diagram, node A is a parent of node B and C. Child node is a node that is immediately connected to the node above it. In this diagram, the node D and E are both children of node C. Nodes D and E are also classified as leaves. A leaf is a node that has no children node. You can think of them as the end of the branches of the tree. Tree nodes also have important properties. Depth. The length of the path from the root to that node. For example, in the diagram, the node D has a depth of 2 because it starts at the root. You have to go through 2 edges to reach it. 2 edges. Height, the length of the path from that node down to a leaf. For example, node C has a height of 1 because it's 1 level above a leaf node. And degree, the number of child nodes each node has. In the diagram, node B has degree 0 because it's a leaf node, so it has no children node. And C has degrees of 2 because it has 2 child nodes. Trees also have a height. The height of the tree is the height of its root node. There's many different types of trees, including binary trees, binary search trees, AVL trees, red-black trees, and B trees. Binary trees and binary search trees are the two most commonly used types of trees. A binary tree is a type of tree in which each node can have at most 2 children, a left child node and a right child node. Yes, this means that the example that you have seen so far is a binary tree. Binary tree is more specific. Search tree is a more specific version of a binary tree with a very particular ordering property. To understand it, first you need to understand subtrees. A subtree is a section of a tree that is a tree itself. In our tree example, node C, D, and E form a tree themselves, so they are considered a subtree. The ordering property of binary search trees establishes that for every node, all values in its left subtree are less than the node's value, and all values in the right subtree are greater than the node's values. The left and right subtrees must also be binary search trees themselves. This ordering makes search, insertion, and deletion operations very efficient if the tree is balanced. A balanced tree is a tree in which the height of the left and right subtrees of any node are very similar to make sure the operations remain efficient. Tries. Now that you know more about trees and binary search trees, let's dive into tries. Tries is a tree data structure used to store a set of strings. Tries are also known as fixed trees, prefix trees, because they are very efficient for operations that require finding strings based on their prefixes. Each node in a trie represents a single character of a string. The root node does not represent any particular characters, so you can think of it as representing an empty string. The node that represents the complete words are assigned end-of-word markers. In this example of a trie with the word top, T, and 10, notice how words T10 share the same prefix, TE, so the data structure follows the same path until the last character, which is marked end of word character in this diagram. This is represented with a red border around the node. So we have T top, T, and 10. The worst case time complexity for a search operation is L, where L is the length of the string that you're looking for, so it's linear. Insertion is also efficient. This operation only requires creating new nodes for the characters that don't exist in the trie yet. The great advantage of this data structure is that when multiple strings share the same prefix, their paths overlap, so the prefix itself only is stored once. This efficiently makes tries perfect for implementing features like autocomplete and spell checkers. However, tries are not efficient for all sets of strings. They can be inefficient if the set of strings has many unique characters. This would require storing many unique characters as individual nodes. These nodes would have to be traversed to find words, which would not be optimal. Now that you're familiar with different types of trees and what they are used for, you can start using them in real-world scenarios. Knowing how to choose the right one is a valuable skill to have, and when you need to tackle challenges in your daily work. So which following statement is true about a binary search tree? All values of the left subtree node are less than the node's value. Every node can have up to 3 children. No. The tree is guaranteed to be perfectly balanced after every insertion. I don't think that's true. It is specialized tree-like structure optimized for storing strings. That is not true. So I think all values of the left subtree of a node are less than the node's value. For which of the following task is tries or prefix trees most effective? For finding the smallest value in a large data set? Nope. Managing a hierarchical file system on a computer? No. Implementing autocomplete? That was mentioned. Storing an unordered list of unique numbers? That's not true. What is the fundamental difference between general tree and a binary tree? A binary tree can only store numbers, while a general tree can store any type of data. I don't think that's true. Binary tree has a root node, but a general tree does not. I don't think that's true. Binary tree has no parent-child relationships, unlike general tree. I don't think that's true. And binary trees restrict each node to a maximum of 2 children, while general trees do not. There we go. General tree. I wouldn't want to fight that guy. All right. Thanks for watching the video. Don't forget to comment, like, and subscribe, and I'll see you next time for our last theory section, and as we get ready for our labs and workshops on this graph section. See you then.